Good evening, everyone, and welcome to the Harvard-Smithsonian Center for Astrophysics. We have an excellent lineup of programs for you this fall, so we're very glad that you could join us. I wanted to make sure you're aware of what's coming up, because in October we are going to hear from Professor John Kovac, who will tell us about Big Bang astronomy from the ends of the Earth. Professor Kovac has traveled to the South Pole more than 20 times in a quest to understand the universe. So he is going to tell us why we have to travel so far to learn about the universe itself and what we have learned from our most remote observatory. Then in November, we have another special treat. I'm sure many of you are aware that in July, the New Horizons spacecraft whizzed past Pluto on a very quick flyby, gathering as much data as it could. Since then, that data has been trickling back to us, and we are being amazed week by week by all of the images and the information that is coming back. So in November, Kelly Beebe from Sky and Telescope magazine will be presenting some of this information to us, along with a nice little history of Pluto and Clyde Tombaugh, its discoverer, in a presentation called Rediscovering Pluto. But tonight, we are going to start our fall off with a bang by talking about exploding stars and the remnants that they leave behind. Now, not every star is going to end its life in an explosion, but the ones that do are actually very important to us, because without exploding stars and the seeds that they spread out into the universe, you and you and you and me, none of us would exist. So they're pretty darn important. Tonight's speaker, Dan Milisavljevic, is a postdoctoral fellow here at the Harvard-Smithsonian Center for Astrophysics. He started his scientific career studying the outer solar system, and then he took a diversion into the field of philosophy before astronomy lured him back. And I think that astronomy lured him back because the universe is dynamic, the universe is beautiful, and the universe is always surprising. So please welcome Dan Milisavljevic.
Wow, Christine, thank you for that introduction, and thank you to the audience for coming out here tonight and giving me the privilege of speaking to you. I like to think of myself as a reporter of the universe, and tonight I get the opportunity to share an extended dispatch of information from the field. Tonight's topic, exploding stars, right? We call these supernovae. And supernovae are among the biggest explosions that we know in the universe, as you can see in this dramatic animation that I've chosen. And so I'm hoping to capture just a little bit of that energy in the talk I give tonight. So let's go right to the important stuff. The bottom line up front is that we as humans have watched stars explode. Okay? Now, stars themselves have been exploding almost throughout the age of the universe, right? Billions of years. But we've only been documenting these explosions for a shorter time. More recently, we had the kind of smoking gun case where we could capture a star and see it explode. Here is Sanduliac -69202 in the Large Magellanic Cloud. Now, it's a relatively bright star at about 20 solar masses and a blue supergiant, but it's not screaming, "Look at me." Only the arrow is letting you know that something is going to happen there, right? And then on February 23rd, 1987, this happened. Okay? Supernova 1987A. Now, A designates that it was the first supernova of 1987. It also reflects the fact that this was discovered in part by a Canadian. 1987A? I can say that because I'm Canadian. Okay. So, although the light first arrived on Earth around February 23rd, the explosion itself took place much longer time ago. I believe about 160,000 years. So around when modern man started combing the Earth is when that explosion took place. Okay? So we had an image of that star beforehand. We watched an explosion, And then we went to it afterwards, years later. And using the razor-sharp vision of the Hubble Space Telescope, we looked at that region closely, and we saw that the star was gone. And in its place, a debris field. Okay? So a star had exploded and vanished. Okay? Now, again, the bottom line up front, why is this important? And Christine already touched on this, but let me revisit the issue. Okay? It's in these exploding stars from which the raw materials are needed for the creation of other solar systems, other stars, other planets, and potentially life. Okay? Anything that's heavier than hydrogen, helium. I'm doing this because I'm picturing a periodic table, if you can think of those two sitting up there, and then all the other stuff there. Most of all those other things, beryllium, vanadium, etc., these are all manufactured in the explosions of these stars. And thus, it's terribly important to understand this fundamental process that goes on in the universe. So again, the iron in our blood, the calcium in our bones, the oxygen that we breathe. Love that oxygen. These are all manufactured in these exploding stars. And thus, as citizens of the universe, I think we should probably know a little bit. In fact, I would say as much as we can about this process. The questions we're going to visit here, after a little bit of setup, are ones that motivate my research. The first is, what are the types of stars that explode? In fact, that first explosion that we had bona fide proof for, the 1987A event, was from a blue supergiant. And that actually contradicted theory. Theory predicted that a red supergiant would explode. Now, theorists, being the way that they are, very cleverly, retroactively predicted that blue supergiants could explode as supernovae, right? They backtracked and they were able to do that. But that was the first evidence that of our, it led us to understand that we don't know the whole story with regard to exploding stars. And then the other question is, how do stars explode? Okay? We have various scenarios that we have drawn up that seem to work well on a general scale. But the devil's in the details, and there's a lot of things that we don't quite understand. All right. Before I touch on these, okay, I want to give everybody a perspective, okay? A perspective of how big these stars are that we're talking about. So I have a little bit of an animation here. Let's go. There we go. All right, so we start with the moon. We're familiar with the moon. Mercury being the smallest planet, Mars the red planet, okay? Venus, I never want to visit Venus. It's far too hot, but Earth. I want to stay here. Now we're going to zoom out a bit. Neptune. You see how much larger it is in the outer planets compared to Earth. Now Saturn, without its rings, the rings are actually make it twice the size. Jupiter, the largest planet in our solar system, and then whoa, there's the sun, right? But wait a second, the sun is actually relatively small. There's Sirius A, the brightest star in the sky. Whoa, now we're getting big. We're getting orange stars, okay? Getting even bigger, Arcturus, we have a red giant. Zooming back some more, Aldebaran, another red giant. And now we're getting to a blue supergiant, Rigel. And then, where are we? Oh boy, you can't see us anymore. So we go back, Antares A red supergiant. We're going to zoom back even more until we get to VY Canis Majoris, which is among the largest star known in the universe. And then this funny part, we're going to go into a very small portion of the star. The horizon looks almost like a flat line, and there's Earth, okay? And we're somewhere on there, very small by comparison, okay? So there's us. Then perspective. Imagine this exploding, okay? That's the context for the talk tonight. Some other background information. It happens to be that the life of a star is largely set, mostly, by the amount of mass it has at the beginning of its life. So let's start with the star most familiar to us, the sun. The sun, which has one solar mass. That's the units of this scale here. Which will last approximately 10 billion years. That's a healthy life, right? Given that the age of the universe is what? Approximately 13.7 billion years. It's comparable to the age of the universe. But you can see as you slowly go up incrementally in mass that the lifespan starts to get much smaller. Here, at say at a jump at 10 solar masses, we're only getting to about 32 million, right? And to 30, and up at 60 solar mass, down to 3 million, which is a small fraction compared to 10 billion years. This 10 solar mass is actually a sweet spot. It's the point at which these exploding stars take place. So that's a disclaimer I want to get up front to you, okay? Stars like the sun will not explode. Yes! That's right. It will suffer a different fate, turn into a white dwarf and actually expand to maybe consume the Earth. But that's a different thing. But it won't explode. And it's 10 billion years, yeah. So it's far away, right? But when you get to this threshold of about 8 to 10 solar masses, that's when you can have this exploding star effect, which we're going to talk about. Also, what's dictated largely by the mass of a star is what it turns into. And I mentioned this already, that stars like the sun, okay, will evolve to turn into a white dwarf. Now, a white dwarf is a highly compact thing. It's a lot of carbon and oxygen that has just been compacted almost as much as you can get it. Okay? And we'll talk more about that in the next slide. If you have larger stars that undergo this supernova experience, okay, about 10 solar masses, you're going to form something called a neutron star. And that's because there's this core collapse scenario. Right? The strength of gravity becomes large enough that you take something that would have been a white dwarf and you kind of sit on it and you make it even more compact. Right? So it's no longer atoms of carbon and hydrogen, but you're down to the neutrons themselves that have been pushed together. Now, if you get very large, and we saw just now what a very large star can look like, the collapse continues until you reach a singularity and it becomes a black hole. So it's from the most massive stars that undergo a supernova explosion that you develop a black hole. And just to give you some understanding of these densities that I was talking about, this white dwarf, if you were to have a teaspoon of this white dwarf, I don't know how you'd come across it, but let's say you had a teaspoon and you're able to walk around, it'd be like holding an elephant in that teaspoon, right? Maybe you could manage it. Much more difficult, nonetheless, would be a neutron star, okay? And I didn't know what to scale it. It'd be about 900 of the pyramids in Egypt at Giza, right? You'd really struggle to be able to hold that out in front of you. And then finally, the black hole, well, that's poorly defined, because density is what? It's your mass over volume. Now, black holes have a mass, an associated mass, but the volume, it's zero. It's a singularity. So any number over zero goes to infinity. And you certainly don't want to hold out a teaspoon of that, because you're going to get sucked into that black hole and ripped apart. Now, this is more of a general take on astronomy, but it's relevant to studying the final phases of these stars, the supernova explosions, is understanding the life of the star leading up to the explosion. This is relevant to understanding the types of stars that undergo supernova explosions. Right? But it's really tough. Stars live a lot longer than we do. Right? I made that point earlier. Okay? And coupled with this is that they're very far away. So not only are they outliving us, but they're so distant. Right? The nearest star, Proxima Centauri, is about 4.2 light years away. So it takes light that amount of time just to get here. We won't be able to visit it anytime soon. So these are problems in time and space. And I just want to do a mental exercise, again, to give you proper perspective of how difficult it is to study these things. I want you to think about fruit flies. Okay? Isn't that a lovely thing? I hate fruit flies, but I love bananas. And I buy bananas every week, and within a couple days, those fruit flies are out, okay? I may not like fruit flies, but some people do. In fact, people in the field of genetics often love fruit flies because they can be a fairly good model for reproducing, say, certain systems related to humans. And humans with a lifespan of about 30,000 days, right, far outlive a fruit fly, which has a lifetime of about a month. So given that, I can go through many generations of fruit flies. I can watch them go from birth to death, again and again and again. You can run many samples simultaneously, right? You can watch potential mutations between them. But now, flip that around. I want you to pretend to be the fruit fly studying the human, okay? That becomes tough, right? There's no way that you're going to be able to watch a human go from birth to death. You're only going to get a fairly narrow snapshot of that person's life, right? And in fact, if you're trying to study stars, as we are in astronomy, that problem is compounded. We're 30,000 days as opposed to 3 billion days around that region, or longer, right? This is for the massive stars, of course, right? So how do you do it? If you're the fruit fly, how are you going to understand the evolution of a normal human? You do it by statistics, okay? What you do is you get together as many people as you can, right? And you try to you try to build a story. Well, you might be able to see there's male and female, and they start off as these small things, and then they grow up. There's this height difference, and they get larger. So maybe you could begin to, but there's a lot of complications. There's ethnicities. There's a pregnant woman, right? It's complicated, right? And in fact, how do you do it? You try to look at as many people as possible. Right? You want as large a population. And thankfully, we have lots of galaxies that have lots of stars in them. Okay? But one also always has to be careful is, do you have enough of a sample size? Right? So for instance, what if you had the population of Boston from which to infer the rest of humanity? Okay? What were the conclusions you draw? Now, Boston's pretty large. It would be pretty good. But what if, say, you had Sturbridge, Massachusetts, as your sample size? Would the conclusions you draw from Sturbridge be different? I'm saying this. My in-laws from Sturbridge and my wife are right here in the audience. Okay, so this is something we have to deal with in astronomy. We try to draw from the largest populations to make the most accurate story, evolutionary, from one star to another. Okay, now, as I said, thankfully the universe has lots of galaxies with lots of stars that undergo many supernova explosions. Now, as it happens, can you hear that? There's a supernova going off in the universe once every second. Okay? Boom, boom. Now, the universe being as big as it is, we don't see most of those supernovae, right? But they are going off. And thankfully, there's enough galaxies within our visible volume that we can monitor them. And on average, supernovae occur approximately once per galaxy per century. Now, what's the strategy? The poor strategy would be to look at one galaxy for 100 years and hope that a supernova goes off. Correct? What you would try to do is look at as many galaxies as you can. So that on average, if you did hundreds or thousands, you wouldn't have to wait a century, maybe within the year or shorter. Right? And that's a strategy. Now, every so often, though, we're in a galaxy, it should have a supernova explosion locally. And it does. Right? Here's a case in 1572, a very bright event. This was documented very closely by Danish astronomer Tycho Brahe, and here's an etching of what he saw. When they're that nearby, they are dramatic explosions, okay? Dramatic events. They can be seen for months, maybe a year or longer. They can be as bright as the full moon. They can be so bright that you can read a book to it, right? And even visible during the day. Now, this is the event of 1572. There was another in 1604. We're kind of due for another one. Right? Now, the thing with our galaxy is that it has a lot of dust. So there may have been, and actually we know, that there have been supernovae subsequent to these events. but we haven't seen them visually. They haven't been so prominent because they're covered by a lot of dust. It's different than when you're looking at external galaxies face on, you can see the disk, as opposed to being nestled within the forest and trying to see through it. Okay? Finding supernovae. This is becoming increasingly sophisticated. And there are many professional surveys that I show here that are doing this. And what do? They image the sky, they return to it weeks later, days later, sometimes hours later, and try to see some kind of change. Okay? Amateur astronomers, people like those in the audience here, also enjoy looking for supernovae, and there's been a rich history of amateurs discovering supernovae. I happen to work with one person, Stu Parker, in New Zealand. He has 2 observatories that he's set up. You can either put your money towards a nice BMW or a good telescope. And so he does this at night, and by day he's a dairy farmer. He's got some 200 cows on his farm, right? And what are you looking for? Well, again, you're looking for changes. In these 4 slides, a supernova is taking place. Looking at it, can you tell where it is? Yes. Oh, really? Very good. Right. Now, it's amazing that actually there's a history. There's one person, Reverend Robert Evans, who actually can do this visually. He can look at look through a telescope eyepiece and know the galaxies so well that he can tell when there's a change like this. Right? I've emphasized the region, but believe me, it's much more difficult when you do it through a telescope. But these days, there's sophisticated software that would take this as a reference image, and then this as a new updated image, subtract the 2, and look for something different, a change. Here's something like it. This is a little bit more, actually, I believe these images are from Stu Parker in his observatory. So there is a galaxy, okay? And you return to it, and you see a little blip, okay? That's what you're looking for. Now, don't be fooled by this teeny tiny galaxy. It's actually very big, but it's just very distant, right? And have an appreciation for the fact that this is an entire galaxy with billions, hundreds of billions of stars, and that's one place, that was one star undergoing a supernova explosion, right? That can reach 1 billion suns worth of energy, 10 billion worth of sun's energy. It's tremendous. Now, when this happens, I have a team of people, this is just a small fraction of them, that we have to jump on the scene as quickly as possible because there's a wealth of information right from when that star explodes as it evolves and enters what we call a supernova remnant stage as the gas continues to disperse. And I have a lot of friends, and they can be all over. They can be running out or near a jet or in the forest or rocking out on a guitar, right? We all work, or scaling a glacier. We all work together using many telescopes, both on the ground and in space, across the electromagnetic spectrum. All right, I think I've done enough of the setup. Let's try investigating some of the questions that I initially posited. What are the types of stars that explode? That animation I showed you earlier gave you some sense that there are different colors of stars. This slide doesn't give it to you, but that animation would have also given the sense of size difference between the stars. And as I mentioned again, that first instance of 1987A challenged the theoretical predictions that it was the red stars. There are actually many other stars that can undergo supernova explosion. Here's the little bit of nomenclature that people need to have some familiarity with. Okay, I'm not going to quiz you on this afterwards. But because we've been able to see so many supernovae, okay, we've been able to find that there are different kinds of exploding stars. Okay? And we do this taxonomy. We classify them based on their properties. And the properties here that are shown are largely dictated by their spectroscopic properties. Okay? What does that mean? It means that instead of just imaging a supernova explosion, at the end of your telescope, you put something like a prism, and you spread that light out into its various colors. It's like if you have a glass of water by the window and you see all the colors of the rainbow, right? That white light from the sun is actually composed of all these colors, and it's being spread out like a prism. Okay? You do this routine for the supernovae, and you see that the light is different. Okay? And based on the patterns of the light, let's call them fingerprints. Okay? Based on the fingerprints of light coming from these supernovae, we can classify them, and we can tell certain physical properties of them. The most important is whether or not they have hydrogen. Okay? If they have no hydrogen associated with them, it's a type 1. And if they have some hydrogen associated with them, then they're type 2. Now, type 2 reflects what we would normally think would be an exploding star. Okay? Stars are primarily, at least they start off as, big balls of hydrogen gas that burn and evolve. Okay? But what's curious to learn is that many explosions don't show hydrogen. So that means that the stars involved don't have hydrogen around them. Okay? As the data became better, we're able to develop a bifurcation here and have type 1a, which have silicon and sulfur-rich explosions, and the type 1b's and c's, which are silicon poor and may or may not have helium associated with them. These type 1a's, they are a different kind of beast. They are associated with the white dwarfs. Remember the elephant density stuff? Okay? They are associated, we believe, with white dwarf stars that are exploding. Whereas these ones, the type 1b C's and the type 2's, are associated with massive stars that are undergoing this process of core collapse, which I'll explain. One more important element between these things, we have a good sense that these are massive stars because they are associated with spiral galaxies like the Milky Way, which have a lot of blue, UV bright stars associated with them. Whereas the white dwarf explosions are associated with both spiral galaxies and ellipticals. And ellipticals are spherical galaxies associated with older stars. Older stars are the ones that turn into white dwarfs. How about some pictures? Okay. The type 1a scenario 1. There's two scenarios that I'll review. You have a white dwarf star, okay, and nearby is some kind of companion star that's pooling material onto it. Now, white dwarfs can live a long time if you don't do anything to it. If you don't reach a threshold of mass at around 1.4 times the mass of the sun, once you do that, you initiate this thermonuclear runaway explosion, and it explodes. Okay? So the white dwarf by itself, hey, I can live just fine. But if you start putting material on me, I'll start to accrete it. And if I reach this magic number, an explosion can take place. Another scenario, and again, so these are two competing scenarios. In the literature right now, we're trying to decide if it's one of these or if it's both of these. Another scenario is where you have two white dwarf stars that circle around each other, and at some point they come together, again reaching that magic, above that magic number of 1.4 solar masses, and leading to thermonuclear explosion. Okay, the core collapse scenario. These are the type 2's and 1bc's. Core collapse scenario is like this here. All right, you have a massive star like the ones I showed in that animation that evolves. Okay? It undergoes a core collapse explosion, which we'll show, and it has associated hydrogen with it. Okay? Another scenario, becoming increasingly relevant these days, is where it's not just one star, but two stars. And they have this elegant kind of dance that the stars follow. And one star can pass material onto another. And it can go back and forth depending on the orbital properties of the stars and their sizes to begin. Right? This is how we believe we get the 1bc's, what I call the stripped envelope. These are core collapse explosions that don't have hydrogen. And how do you remove that hydrogen? You have some kind of companion that removed it from you. And then, in this case, one star had its evolution evolved, and then now we have another star on its own. It continues to evolve. This is around 20 solar masses until it undergoes a supernova explosion. Okay? These are the types of stars that we think undergo the explosion. I had a slide in here. I like to call this dancing with the stars. Okay, next part. How do stars explode? This is where the physics comes in. Okay? And I have to visit this a little bit, but hopefully we can hold each other's hand as we guide through this. Stellar evolution. The star begins as primarily hydrogen, some helium, and trace amounts of other elements. Starts as that, okay? Now, because the star is so big and it has such large gravity, at its core it's really hot, and it can undergo nuclear fusion. Now, this is different from what we do on Earth, nuclear fission, which we take something like uranium and we split it apart. Okay? Fusion takes lighter elements, hydrogen, puts them together, produces helium. Okay? This will continue in the core until that supply of hydrogen is run out. And then it works on the ash of that process, so the helium. So it starts to burn helium. Temperature goes up. Okay? Once it goes through that supply of helium, goes to the next element. And it continues in this way. Now, if the star is large enough, and again, that's this magic number for the core collapse at around 8 to 10 solar masses, iron will be produced in the core. Now, something changes with iron. When you have iron, the process of fusion is no longer radiative. It's not exothermic, it's endothermic. It robs the core of that radiative pressure that was holding it up against the tremendous gravity. And there's a collapse that ensues. Okay? This collapse continues until the neutrons come to a point where it says, I'm not getting any smaller. Can't do it. Right? And the material, the rest of the star says, whoa, where am I going to go? I got to go out. And that's the explosion. Okay? So this neutron star, proto-neutron star is made at this point, and the rest of the material bounces off of it. And this is supposed to be a supernova explosion. Now, a couple of caveats. One is that if the star is truly massive, then this infalling material will be strong enough to continue the collapse. Okay? And that will ultimately produce a black hole. Right? For the largest of the stars. Now, a funny thing about this process of this implosion-explosion that should take place in the majority of massive stars is that we've tried to simulate this using the fastest computers that we have on Earth for decades, and it's just failed. They've all collapsed. Okay? Now, fine enough, we predict that there'll be black holes. That's fine. But I showed, the first slide I showed you, we know that stars explode, right? You can't hide from that. And so there's something missing in our understanding of massive star explosions. So how do you investigate a process that takes place, this core collapse process happens in less than a second. Less than a second of something that's lasting 3 million years, right? Inside of this massive star that is very, very distant, most often the case in other galaxies. What you do is you try to be clever, okay? And you use nearby supernova remnants. This here is the remains of a star that exploded approximately 330 years later. Okay? It's in the constellation Cassiopeia. And Cassiopeia A, it wasn't Canadian, Cassiopeia A, this means it was the first radio source detected in this region. Okay? Look at this. This is what the ejected remains of a star looks like after a core collapse process. And so what we can do is we can be clever, kind of like a bomb squad investigation, and look at that, how those remains are scattered and try and understand how that explosion took place. And this is something that I've been actively working on. And here's a web page in case you want to investigate this. I have a little bit of an app. I made this is not simulation, this is real data. I made a three-dimensional reconstruction of that debris field to see how the certain parts of the star went off. Okay? Think of it like this, okay? Bomb squad investigation. you're told to go into, you're going into a room where a bomb's just gone off. What's the first thing you do? First thing you do is you look and you see, well, where's all the debris? Did it go in all directions? Or is there some preferential access, like in a pipe bomb? That tells you something about the dynamics. Next, you're going to go and scrape off the pieces that you find. And you're going to do some kind of chemical analysis. You're going to find out what that bomb was made of. Right? That's what I'm trying to do here, where we have a three-dimensional reconstruction of the gas as it's been ejected. And we can follow that up with spectroscopy to do a chemical analysis to know not only where the stuff was ejected, but what is the material that was ejected in certain places. And what we found in this case is that the explosion must have been fairly turbulent. And there's a great headline: radioactive bubbles may have punched holes in supernova's heart. We have evidence that this supernova explosion had plumes of nickel-rich material. Nickel is a radioactive element. Okay? The explosion itself was fairly turbulent, and that may be reflective in the explosion geometry, how that explosion took place, or the star itself. So what the explosion was exploding into. On the left here is a simulation, and here is the observation. So what I do is I work with people who run these simulations and say, hey, this is what the end result is. In this case, the nickel-rich material is represented in the blue, and the red is sulfur and oxygen-rich material that we see in the optical. And we can see these blue regions here. This is nickel-rich material several hours after the explosion. And you can see that they're racing out ahead of the red, which is oxygen, and the green, which is carbon. So somehow, the heavier elements were shot out ahead of the lighter elements. Right? That's something that we're actively trying to understand, where that seed of asymmetry began. Here's another cool thing. This is, again, something that I didn't think would happen when I started school on this subject, because I was in school about 24 years as I did it. 10 years ago, this was not the case, that stars sometimes have eruptions shortly before they explode. Okay? Why is this incredible? In that the star being so massive and lasting so long is fairly stable. Okay? So I was taught that whatever happens in the core happens there, and none of that information gets transmitted to the envelope. But in this case, right, the star was signaling its death. It was burping, saying, oh, things are happening to me in my insides. They're all twisted inside. Here is T0 is the time of explosion, the supernova. Look back in 2009, and that's actually the event name, 2009 IP, which is silly, because a supernova actually took place in 2012, right? But in 2009, there was a jump in its brightness, and we thought a supernova was taking place, but it wasn't. This is what we call a supernova imposter. And this is associated with some kind of outburst. And as the star was continued to be monitored, the light curve, you can see a little bit of fluctuations, a lot of jumping around here in 2011, until we reach 2012, where there's this double peak explosion. Right? The remarkable thing is that this means that we can actually predict when the star is going to explode. All right? Again, the time scales associated that this is happening in the last year, which is just such a small fraction of the star's entire life, is amazing. Now, there are some stars that we know can have these eruptions. Here's a dramatic example of Eta Carina. You see these lobes. That was a previous mass loss event. In fact, in the 1840s, this star, which went from being barely visible, went to being the second brightest star in the sky for years. Okay? And then it faded to being no longer visible anymore. This was long thought to be only a transitional stage in a star's life before it evolves to something else and lasts 100,000 years. Again, long lives, you'd think, slow transitions. But it seems that this kind of eruptive activity can take place on much shorter timescales leading up to the star's death. So I showed this slide just a few minutes ago, right? And I was describing the evolution of a star as it goes through successive stages of nuclear fusion. And I showed this onion skin interior. What we're learning, largely from what I just showed you, between the turbulent explosion and the eruptions prior to the explosion, is telling us that we have to go back to the drawing board. Something about this is wrong, at least in the stages leading up to a supernova explosion. Okay? While this may hold for the majority of a star's life, and it should because it's stable, at some point there may be turbulent activity. The insides are getting mixed up, right? Preluding the ultimate demise of the star. Okay, I see some younger potential budding astronomers, and I want to just mention some future research that people can do. These are observatories that I may get to use somewhat of, but these are more geared to the next generation. Here's a large synoptic survey telescope. This is going to be imaging its visible sky every few days. And it's going to have a tremendous pipeline. It's going to go very deep. And they anticipate finding maybe 100,000 supernovae per year, which is crazy. We're now maybe in the hundreds. Okay? So remember Boston versus Sturbridge. You know, that may be a scenario that we're in. We may have a much larger sample we will have a much larger sample to draw from. We'll be able to follow up these supernovae with the next generation of telescopes. Do you see that person? Okay. The largest telescopes now are about 10 meters in size. These ones are going to be 25, 30, maybe 40 meters in size. Okay? You'll be able to go much deeper with much greater resolution than we had before. And we'll be able to look at it with new frontiers of wavelengths. So here we can see the advanced LIGO, which is sensitive to gravitational waves. Okay? This is something posited by Einstein's general theory of relativity. Remember, mass influences the space around it, and certain supernova explosions and mergers of their products, merging black holes, for instance, are thought to be strong, relatively strong generators of gravitational waves, and we may be able to find in that way. And then finally, just perspective to wrap up here. In the winter, as you look up in the sky, and maybe you're finding the constellation of Orion, the Hunter, and look up in the shoulder, look towards the star Betelgeuse, which is a red supergiant. Yeah, now, as you look at Betelgeuse, perhaps you'll have a new appreciation of it. Right? You can appreciate that it's about 1,000 times the size of the Sun, that its mass is about 3 to 30 times the mass of the Sun, and because it's a red supergiant, it's nearing the end of its life, right? Which is long compared to us, but relatively short compared to the age of the universe. And because it's in that stage where it's close to the end, right? It may be undergoing core activity that's turning its insides out, that may translate into outbursts, right? Preluding the star's potential death, right? And in that death, it will eject copious raw materials to seed new stars, new planets, and maybe life, right? And maybe, while you're watching that star, right, or maybe 10,000 years in the future, the light from that explosion will be visible to you, right? But thankfully, from the safe distance of the Earth. Thank you very much. That's all.
All right, I'll bet that there are some good questions out there, and there's the first one right in the back, sir.
Stars, binary stars, are they usually, two-part question, are they usually both the same type? That's the first, and are they accreting all the time also?
Great question. So there's a lot of flexibility and parameter space between the stars. And in fact, no, they don't need to be always the same. Because they undergo this swapping of material, that will change the star. One will become red, one will be blue. They actually go back and forth. And actually, there's a few binary systems that you can look through in a telescope. You can see two different colors of stars nearby to one another. And your other question was?
Are all binary stars accreting?
No. So, in the sense that sometimes binary stars are far enough that they never interact. Okay? Sometimes they're near enough that one has to evolve to the sense. Generally, in a massive star, towards its later stages, when it leaves what we call the main track, when it starts to burn helium in its core, okay, it starts puffing. Things happen. And when that puffing happens, it can pool material into the other star. But that doesn't always happen. Right? It's not always happening.
Thank you.
Right up there, sir.
Yeah, the original supernova that we were talking about during the lecture, the 1984A. What was the size and type of that one?
So that was a blue supergiant, approximately 20 times the mass of the sun. 1987.
How far away is that from Earth?
How far away is that?
Yeah.
So that's in the Large Magellanic Cloud, which is approximately, that was the number that I used, 160,000 light years away.
Yes, ma'am.
If the largest known star is supernova, how wide would the spread be and how bright would it be?
Oh my gosh. That's,
We want really big explosions here, Dan.
yeah. How big can we make them, right? Well, in my short amount of time, I couldn't cover all the varieties of supernova. And in fact, there is a class, we're running out of superlatives, so it's called superluminous supernova. You think I'm making this stuff up, it's real. It's exciting science. And these are actually 100 times brighter, generally, than the supernova that I'm talking about here, right? And that's really big. As far as the amount of space that it will take up, wow. I know in the case, remember that Cassiopeia A? Do you remember the remnant I showed in that 3D reconstruction I did? So that has a radius of order, I have to do the numbers in my head, 4 parsecs, multiply that by 312 light years, and we're going to go. So it'll evolve, and then I'm going to say kilometers, and that's tough. Really large, really large. Yeah, I know, but I'm trying to put it on physical scales, but it's very large. But we can talk afterwards more about that, but it's a good question. I like how you think, big.
We have, yes, and then I'll head over.
Hi, my question is, so you were talking about the binary star systems, and so there's a white dwarf and then there's a larger star. The white dwarf is taking on the material of the larger star, and it gets to a certain point and then it novas. Does the white dwarf manage to survive that? I've read that it can actually survive that.
Great.
Even though there's an explosion.
Great question. So you said nova, and that was what we'd long known before. A nova is this cataclysmic variable situation where the white dwarf is accreting material from the companion star, right? But it reaches a certain mass in which there's an explosion, and you're correct, it survives that explosion, okay? And there's these systems where it happens again and again, routinely, right? That's a nova. The supernova is when that white dwarf actually explodes. Very good.
Over here.
So that the 16th century supernova observed by the Dutch astronomer,
Tycho Brahe.
it's so close to today that it should be recorded by more than one civilization. Do you see that in history?
Which it is. That's right.
How many civilizations?
And see, that's very good. So Chinese had very good documentations. Korean had very good documentation. Those are sources where we look for historical recordings of supernovae. And in fact, I want to mention that that's a very interesting aspect of astronomy, archaeoastronomy or historical astronomy, looking at ancient records to find when people had recorded these events.
over here, and then I'll head back over there.
I'm
Yes.
just curious about the distribution of like exploding stars versus, or potentially exploding stars in the non-exploding. Like what percentage makeup would be the one?
Oh, okay, very good. So there is a distribution function, and I won't put it up because I don't have it handy. But the simple answer is that there's a lot more sun-like stars and smaller than there are than the massive stars. Okay, a lot more. And it's funny enough that the massive stars produce much of the light that we see in a galaxy. Okay, but the fact is, just by numbers, there's plenty more of these solar-like stars and smaller, actually.
Do you have any sense of it to be 1%, 10%?
You know what? I'm going to make a number up, and so I'd rather. I'm thinking less than 10%.
Fair enough. Yes, and then I'll head over there.
Do you see any impact on nearby stars?
People
Driven by
look for that. Yes, that's an excellent question. People look for that signature, right? So in trying to understand the various scenarios that have been posed, the types of stars that explode, there have been claims of seeing the signature of a slight bump in the light curve, right? As we watch with time of a light curve of the supernova that would be represented by, that would be reflective of the shock of the supernova running into a companion star.
any chain explosions?
No. No. Well, you know what? I may have it here. I'm supposed to be swift with my answers, but this made the Huffington Post, so maybe I can find it. Let's see. Yeah, right here. Okay? So, what was amazing about this supernova, 2013 EK, Eek! All right here, which actually was discovered by Stu Parker. All right? What was tremendously cool about this event is that a year previously, supernova 2012 happened at exactly the same location. Okay? So, I'm in the process of writing up a paper trying to understand, could there have been some kind of chain reaction? Were the two related? Is it the same system, maybe? Or two stars that were nearby? So, excellent insight there. Oh, and I mentioned it just because it was one of 27 of the most mind-blowing space photos of 2013 will put your life on Earth in perspective.
So you need to put his name on your paper.
well, let's collaborate now.
Yes.
Yeah, so you had mentioned type mechanism for type 1a supernova, type 1b, C, and type 2. I also read about this other type of period stability supernova, and I tried to understand the mechanism, but I couldn't quite get it.
Yeah. I'm of the same page as you. We can talk about it afterwards. I have some understanding. It happens in a certain subset of stars with a certain mass range between, I'm going to make this up, between 60 and 120 solar masses. There's a certain mass range depending on certain properties where there's this pair instability. It's another path that allows the explosion to take place. So we could talk about that afterwards, but that's very interesting. Again, it's trying to understand all the various ways that these explosions of stars can take place, and the pair instability is one that's been increasingly popular.
Okay, last question, gentleman, right on the edge there in the yellow shirt.
So, what type of star and what type of star, when it dies, would end up in a magnetar being formed?
Oh, so a magnetar. First, so everybody's aware, a magnetar is basically a neutron star with a large magnetic field. So, magnetic fields are generally associated with a rotating star. So, stars that had some kind of rotating core at the time of core collapse would be ones that would give way to the magnetar scenario. And magnetars are invoked often to power the luminosity of a supernova that we see. Somehow this rotational energy is transformed into luminosity. And some of the most powerful, these superluminous supernovae, may be powered by magnetars. I like how this is coming together.
All right, thank you all once again for joining us, and I wish you all a pleasant evening.
Thank you.